Okay, good evening, good afternoon, and welcome back to the session that we had yesterday, and this is the continuation of what we had been doing yesterday. Okay, we were on chapter 6 yesterday. On chapter 6, that we talk about that the last thing that I was talking about was that Cisco. Okay, and before we came to the Cisco, you can remember we were talking about several things that related to that residual. Remember? The residual is nothing but this one, y minus y bar. Then sum of absolute residual is by taking the absolute value and then sum them up. And then sum of squared residual means like instead of that absolute, you're going to square the residual and then take the sum. Then you're going to average it. Sum of squared residual average by dividing by n minus 1. That's called the average squared deviation. See, average squared deviation. That's a, see, in another name, mean squared residual. See, mean squared residual, variance, s squared. This one, or average squared deviation. See, average squared deviation. When you say average, that it has been, you don't have to say about the sum because the sum has already been absorbed into the average. In that day, you don't have to worry about that telling average anymore. But the sum divided by the this value is called the average. That's the average square deviation. When we took the square root on that one, that's a standard deviation. S or this one, or we can say average deviations, or root mean squared residual. See, root mean squared residual, or average deviations. See? These are average deviations now. Or now last thing that we were talking about, the residual divided by the standard deviation, which is y minus y bar over s. That's called the standard score or C-score. In another way, C-score, that's where that we stopped yesterday. So we can talk about this one in detail more. C-score is like how far each data point is away from the mean in terms of standard deviations. Or you can say how many standard deviations each data point is away from the mean. See how many, see, standard deviations each data point is away from that one. Or deviation divided by standard deviation. It's like a comparison between a deviation and a standard deviation. See how many standard deviations for, see, for deviation. See, comparing deviation of a point of a data value from the mean with the standard deviation. See, the standard deviation. See, oh, sorry, with the standard deviation. See, with the standard deviation. See, standard deviation. Or on the other hand, when you have a data, you can draw the histogram and then you can keep the mean at the center and you have a standard deviation for that particular data set. And then instead of working with that one, you're going to go ahead and standardize that one. That's called standard data. Once you standardize by taking y minus y bar divided by standard deviation, then you're going to come up with another kind of a distribution or histogram. Then that's a graphical representation of the distribution. That distribution has a always, okay? See? He has always a distribution, always, okay? This one always. Mean 0 and standard deviation 1. Those are standard values, okay? That's where we stopped last time, and then let's get back to and then continues that discussion. Okay, we were talking about that one. Now they were telling that, okay, let's apply this one for that. If you have that certain data point, 65.1 millimeter thumb length, if you want to standardize that particular value, how do you do that one? First, you're going to go ahead and run that favorite statistics in order to get the mean and standard deviation. And let's do that one and then save into Z. I'm going to say I have 65.1 minus, I need the mean. I'm going to go to the thumb stats. It's like my now data set. And then I'm going to go ahead and mean is like my variable now. Go ahead and call the mean. See? Divided by standard, you go to standard deviation, you go to thumb stats. Inside the sum stat, again, standard deviation is like a variable. And then I'm going to run Z. What would we give this one? Instead of 65.1, it's going to be that above the average. See, can you remember 62, 61 point something for the average for the sum data? That data that it's away from that one, like how many, see, if you have a 61 point here, 61, let's say that this one is 61 point something. Okay, should be 61 point. We can check that one too. Okay, we can run stats, sorry, thumb stat, dot stats. It's mean, and then I need the stats. And the deviation as well. See, it's the mean 60.1. 60.1. Standard deviation is 8.72. Let's say 73 to 2 decimal places. The other one, 10. So I'm talking about this one. See, that's the y bar. See? So the y bar, that means that if I'm going to throw this one really on this side, let's say that my convenience, I'm going to get this one, okay? Something like that, okay? At the center, you have a mean is 60.1, standard deviation, which is S, sorry, that one going to be 8 point something, okay? It is 8.73. 8.7. See, this is y bar. 60.1. This is S. 8.73. This is for y. Now instead of y, if I draw this one for C, as I said earlier, it's going to become 0. The mean is 0 for sure. Doesn't matter whatever the data set that you are playing with. Doesn't matter, but still is the mean going to be 0 because it has been standardized. See, how do you standardize? By each and every data point, subtract from mean and divide by standard deviation. We have a very particular value we were talking about here, 65.1. See how much it is above that one. We already saw, see, 0.57, 0.57. 65.1 in the Y distribution, but when it's come to the Z-score, 0.57 above the mean. See, look at, that's the Z-score, that's the C value. C equals 0.57. See, like that. This is the code. Okay, which is the correct interpretation of the Z-score? This thumb is bigger than 0.57 of all thumbs in the, no, this thumb is 0.57 standard deviation, less than 1 standard deviation above the mean. That many standard deviation, thumb length is this many standard deviation above the mean. This many standard deviations, okay? It has been given in terms of standard deviation. That's what we call the Z-score. Okay? See, you can compare different distribution with the aid of Z. You have a 45, that's a score. You're going to subtract this one and divide by that value. This minus that divided by that would give this one. This minus that divided by 5 give you this one. See, now you can compare and see which one has the better value. See, looking at the Z-score help us to compare the abilities of these two players. Even though they play games with the different scoring system, based on the Z-score, we could say that because it has been brought into common ground, even though that they have, see, Argyle and Spargyle players, see, this guy has a score 45, this guy has a 65, doesn't mean that he's playing poorly. It depends on that average and the standard deviation of that particular data set. This one, see, larger standard deviation, see, he has a 2, 3, so that guy is playing, see, Spargyle player is playing very good. See. So let's see, modeling the shape of the error distribution. Now let's go ahead and pay attention to the error distribution. See, you can remember that error term is same as the same as the original data distribution. See, we quantify error because fundamentally it tells us how well our model fits the data. See, when our model is the mean, calculating of sum of squared, residual or variance and standard deviation are useful because these are all minimized at the mean. See, and minimizing error is our #1 priority as a statistician, I mentioned. The less error, the more variation is explained by the model. See? The less error, the more variation is explained by the model. When you have the less error, that more variation can be explained. Quantifying error also gives us a way to put deviation in perspective. Okay. No matter what the scale of measurement is an outcome variable, standard deviation is a convenience way to assess in how far a particular score above the below the mean, especially when it's incorporated into C-score. In the C-score, you know that how we did that. But as useful as it is quantify how much error there is, it is also useful to model the shape of the distribution of error. Not only the error, we have not only quantify, we're going to look at what's the shape of the distribution, especially if we want to make a better prediction about future randomly sample observation. Although the mean is the best point estimate to the mean of the DGP and the best predictor for future observation, if we must choose a single number, we can make more accurate prediction if we are willing to make some assumption about the shape of the distribution, error distribution. See? For example, if you are willing to assume that the distribution of a variable in the population is symmetrical around the mean, see, I'm talking about, see, variable, see, that's the distribution of a variable in the symmetrical around, okay, population, okay, not the sample. Then we can predict that there's like a 0.5 probability that the next observation will be above the mean and 0.5 chance that it will be below the mean. See, since it's symmetry, the population distribution, okay, I'm talking about population. See, assume that the distribution of a variable in the population. So, see, look at here. Take a look at the two sample distributions above. See, these are sample distributions, okay. Even the population, that's the same thing, okay. Variable in the population symmetrical around the means, okay. So this one, instead of talking about with respect to the population distribution, now they're gonna say they consider this one as sample populations, sample distribution. So mean both distribution is 100, see, in both case, okay. Here they see, if for example we're willing to assume that the distribution of a variable, see, they both have, see, the mean of both these because they both appear roughly symmetrical. It's assumed that the DGP that produce each distribution would, in the long run, produce a perfectly symmetrical population distribution. See. But if the mean of the both distribution 100 because they both appear roughly symmetrical, let's assume that the DGP means the population that produce each distribution would in long term produce a perfectly symmetrical population distribution as well. Since these are symmetrical, we're gonna assume that they are coming from a symmetrical distribution. Since this is symmetrical, they think that it's coming from a population symmetrical distribution. This is a sample distribution. This is a sample histogram. This is a sample histogram. But they believe these are coming from even the population has a pretty much the same kind of a shape. Okay. Now make a prediction. If one new randomly select observation were added to each of these samples, in which sample would the new observation be more likely to be greater than the mean? See, both are equally likely. See, both are equally likely. See, if you add a new one, see, new data point, see, new randomly select observation added to each of these sample, in which sample would the new observation be more likely to be greater than the mean? In which sample would we have the more likely to be greater than the mean? See, That's why they ask the question. See, from what would be the set in which distribution, means sample, in which sample be here or here, would the new observation be more likely to be greater than the mean? Greater than the mean. New one, greater than the mean. See, both are equally likely. See, if we assume that the both of the DGPs produce a symmetrical distribution, then the both are equally likely to produce a next observation that it is greater than the mean. See, if we assume that the both of the DGPs produce symmetrical distribution, both of the DGPs, okay, both of the population produce that these kind of distributions, we think that now next one gonna have a, like a chances of equally likely chance of that for both, okay. So that's why they say over here, some people might say that DGP for sample 2 is more likely to produce an observation above the mean because the DGP is more likely to produce a larger number than the DGP for sample 1. But no, it is more likely to produce a smaller number than the DGP sample. Both distribution have 50% chance of producing the next observation above the mean. If you are willing to make a more detailed assumption about the shape of distribution, we can use the assumption to calculate the probability not just of the next observation being above or below the mean, but also the probability of the next observation being greater than or less than or any other score, not just the mean. See? So they were talking about here very interesting thing. They were thinking by looking at these distributions, okay, they say that there's a chance, okay, there's a chance. See? For example, we are willing to assume that the distribution of a variable in the population distribution, okay, from which that these two distributions are generated. See, two sample distribution above. These are two sample distribution, but both distribution have 100 mean. Okay, but on the other hand, say that if you assume that both of the DGPs produce symmetrical distribution, both of the DGPs produce symmetrical distribution, then the both are equally likely to produce a next observation that is greater than the mean. See, they are equally likely produce the mean, produce that next observation that is greater than the mean. That's what they say. They are equally likely. They both. If one new random select observation, in which sample would the next observation be more likely to be greater than, see, in which one? If you add another one, it's going to be more likely to be in this one, not this one. How could we know? When you're going to add a next observation. Next observation going to be definitely like on average, it's going to be the mean only. See, the mean only. But they were saying if it is more than mean, what is the chance that in which distribution it will contain that this one? It is equally likely. Equally likely means either here or here. See, 50% chance it's going to be here or here. Either it's going to be go to this guy or this guy because of the mean. See, it's equally likely. See, the next observation is more than 100 is going to be in this distribution or this distribution. You pick another one and see that it's might going to go to here or here. They say they might going to go to either here or here with the equal probabilities, equal chances, like a 50% chance. That's why they say both are equally likely. Both are equally likely. So if you assume that the both of the DG produce symmetrical distribution, then both are equally likely to produce a next observation that is greater than the mean. They are equally likely to produce. Either this one or this one will produce next observation gonna be more than 100. Okay, that's what they say. Some people might say DGP for sample 2 is more likely to produce an observation above the mean. See, above the mean, but that's not the case. More likely to produce a larger number than the DGP, but no, it is also more likely to produce a same smaller than that one too. See, than DGP sample 1. Both distribution have a 50% chance of producing the next observation above the mean. See, What that means? That means that if I explain this one very clearly, this is what they were talking about. Okay, they say that. Okay, I'm gonna put this one. They say this is what they were talking. They say they have a two distributions. Okay, one is more more clustered data, more clustered around the mean. The other one little bit spread out. Okay, a bit spread out. See, it's spread out. See, flat and spread out. See. This is, let's say, sample 1. Sample 2. See? In which distribution they say that they both have 100. Okay? Mean 100. In which distribution will contain more than 100. See, if you're going to add another one, add new observation, see, in which distribution would contain the, see, see, here. See, in which sample would the negative distribution be more likely to be greater than the mean? More likely to be greater than mean. Which one more likely to be greater than mean? Greater than mean. Okay, let's say that in distribution, what is the chance of any distribution going to be more than 100? Chance of being more than 100, more than mean. It's how much? Half or 50%. See, this one is, if you go ahead and look at this one, see, it's 50%. Assuming that symmetric, okay? Assuming this is symmetric, you know, okay? Symmetry. 50% on this side, other 50% chance of being in the below 100. See, so does with this one. I'm gonna assume this one symmetric as well. Again, I'm gonna say, what is the chance of being more than mean, which is 100, in this sample is half or 50%. See, they both would have the same equal chances of being more than 100. That's what they say. Okay, so they both sample have equal chance of having a new observation more than the mean. That's why they say equally likely. There's an equally likely chance that new observation is more than 100. They are talking about this guy. Okay, this one, this half. See, this area is 50% in this case. Also, in this case, also 50% in the sample 1. That's why we have like a 50% chance of the 50% chance that new observation being more than 100. Therefore, we can say they both equally likely have a chance of having that one more than 100. The next observation that's crazy. Therefore, both are equally likely to produce a next observation that's greater than the mean. They are equally likely, produce a new next observation more than that. They say that later on. Not only that, we can talk about that not more than mean only, we can talk about any particular valley and see whether the area is going to be the same or not. That's what we are trying to discuss here. Okay, that's what they meant over here. Okay, they're not talking about the same distribution. They were talking about if you go ahead and look at the distribution and see that whether this distribution will produce a new observation that is more than 100. What is the chance of producing more than 100? It might gonna be more than 100 anywhere. See, more than 100 would be anywhere being covered by 50%, because altogether this chance is 100%. So there's a 50% chance that new observation, that this one will generate a next observation more than 100 is 50%. Then this distribution produce next observation that is more than 100 is 50%. Okay, write this something. This distribution produces a new observation that is more than the mean is 100. Yeah, 100 with the 50% chance. Okay, 50% chance. Same way over here, this distribution also produces a new observation that is more than the mean, which is 100, with the same chance of 50%. They both would have 50% chance. Therefore, in both cases, they both produce new observation. See, equally likely. They both produce equally likely new observation. Therefore, put together, you can say they both, see, the both distribution equally likely. Therefore, both distributions, okay, equally likely produce, okay, this means distribution, okay, that abbreviation, produce new observation that is more than the mean, which is 100. Okay, if this case is considered being more symmetric, okay, that's what this is. Now calculating the probabilities. Now that's the same thing. Okay, this chance means the probability. We are heading towards the probability. So this is nothing but the probability. See, this is a distribution one. See, sample one distribution. See? I say more than 100, more than mean. I have a 50%. 50% is nothing but, you can say, area under the curve. Is area under the curve, or probability that the new observation is more than 100. That's the probability. Newton probability means chance. See? Chance, same thing. Chance, see? That's what they are trying to calculate. See, now they are trying to calculate that area under the curve. How do you calculate? See, one way to get this probability distribution is to use the distribution of data. Recall that we use the mean of a distribution, probability distribution. See, mean of distribution data and estimate for the mean of the population. In a similar fashion, we can use the portion of cases that within the certain region. Okay. Here is the code to do that for a data frame called the sum data 2, which holds the data for sample 2 shown in the histogram above. Okay, some data for this histogram 2. So sum data 2, you're gonna say something called greater than 110. Mean some data outcome is greater than 110. You're gonna double check. See, it's a comparison. You go to the outcome, that's the outcome. See, you have an outcome variable in this data set. That outcome is that whatever that values that they were thinking about, these are the outcomes. See, these are the outcomes. These outcomes, they're going to go ahead and check whether this is going to be greater than 110 or not. These are Boolean. We know that one. Okay. If they are Boolean, that means you're going to get true or false. And you select this guy, and this guy from that particular data set. And then if you print, you can see this is greater than 100. See, outcome greater than 100. Greater than, I'm sorry, 110. Not 100, 110, I'm sorry. 110, false. Greater than 110, false. Yes, right there. It's always a good idea to look at the data to make sure that your code did what you thought it was going to do. In this case, it looks like it did. You can see that for row 1, the value of outcome was 100.97762, which is less than 110, and the value for greater than is false. Okay, you can check that one. So the same way, next we need to get the tally of these true and false. Write the code to get the tallies of greater than 110. How to get the tally of 110? See, that name is greater than. See, the variable name is greater than. See. Okay, then copy and this one. Okay. Let's check this one first. The tally. Go to that data set and check that one. See, true, how many truths? 101, 399, gonna be false if you keep going and then get the whole data set. Okay, then you need that one in proportion. Then say tally, same thing. Okay, tally. Instead of that one, they need the proportions. Okay, they need this one. So this one, we're gonna go ahead and say format. You need proportions. In proportion. Proportion. Format, proportions, and proportions. Must be tally. Okay, I'm gonna do this way. So tally. Let me get this one. Data. Proportions. Is that proportion? Proportion or proportion? I think it's a proportion. So you can get the proportion. Some data gonna come from this one. Greater than 100 from data. This one greater than 110 in data. Then format proportion, not the proportion, okay, greater than 110, data name is some data to some data to, you get the field greater than 110, no, X must, len must be atomic for sort list. Have you called sort on a list? Okay. Why that takes some data to greater than 110. Okay, this one tally, get the tally in proportions. Okay, format proportion. I get the proportion. I get this one. I get this one. Greater than 110. That's the variable. Greater than 110. Some data to. And value of outcome. Data to. Oh, okay. The original one, they have to go to. No, let me see. They call this one, see, greater than this one. See, some data, select some data, outcome. Not the outcome. We need the tally in proportion. You see, tally greater than 110 in some data too. See, the proportion, some data too, is the variable. There's a new variable. See, greater than 2 in some data set. No. That's not working. No. Some data 2. Some data to format the spellings here. Sorry. Yeah, that's the problem. Sorry. Format proportion. Yeah. See, if you want, you can write like this. Too should be. See, you notice that there's a mistake with the proportion. The spelling say okay, tally. Same way like this. Copy and then change the format rather than writing like this. Should work too. See, should work too. Then it's gonna say X. If you particularly say that about that variable name greater than, then it will show this. And there was a mistake over here. My spellings, yeah, format. See, proportion. Okay, they will give you 0.2 and this one. See, the way. Then see, trying it with the fingers. See, let's apply these ideas to the empty model as we created before fingers data frame. The empty model we model thumb length as the mean. This one. Plus error. The error can be either be modeled as the residual around the mean, no, as the variation around the mean. In either case, the distribution is same, except that when we model residual, the mean is going to be 0. See? So what they're gonna do that we're gonna do the same thing, that the proportion and see how much would be that this is the proportion, this is the probability. See, this is the probability. The probability, if you add the true ones and the false one, they would give you, see, 0.798 plus the 0.202 will be the 1. Okay, the same way over here, the number, any number that you pick from that particular data set How many would be greater than 10? What's the proportion? What percentage of data will be more than 110? More than 110 is the we call the, see, probability. See, true means that's the amount that more than 110. See, some data, that data set name is some data. See, it has a variable because it has been set into a data frame. See, data frame name, this one, this is the variable. Data gonna contain within this guy, but it has been put it into a frame called the sum data too. And then see that how many of the variable, how many data points are more than 110. Then we got the true false, and we calculate the how many true and false. And instead of going to that number of them on 101 and 399, 101 divided by the total of this one, which is how much this one, 400, 500, no? 500, that would give you this proportion. See, that's the probability. That's the probability. They were trying to use the same idea here. See, they're trying to use the same idea here. So this is some kind of a distribution. You have the mean at that point, and then you're gonna looking into a certain value. See, modify this to create the Boolean variable that record where the thumb is greater than 65.1. 65.1. I'm looking for this area. See, this area, how much this area would be. How do you find it? This is the way how you're going to find it. You go to the fingers, greater than 65.1. So how do you set this up? We can use the same technique we used over here. Excuse me. I'm going to go ahead then. Okay. Then I'm going to go ahead and give the name of the data frame fingers. You know the fingers. And the fingers, we were talking about thumb. Okay, thumb. Thumb. Here they were asking about 65.1. Okay, 65.1. See, and it has been assigned to this guy. Now you're gonna get the tally. What would be your variable? Variable is thumb for sure. Thumb. What's the data? Fingers. See, the format proportion. And run. See, proportion of greater than this one. Thumb. See? So if you go ahead and find the tally, see, 65.1, it came like this. So that's for the fingers, okay, individual fingers. For this one, since that our new variable is this one, okay, I'm gonna run this one in another way, the way that we want, okay. We're gonna put this one, see, tally. This way we need that which is thumb. Now data set is fingers. My new one is called not the thumb. See, if you want, you can check the thumb individually or together. All you're gonna check and see that how many of thumbs greater than this one. See, as a proportion, it's gonna be 0.19%. This one is almost 81%. This is 20%. Sorry, see, 20%. This is 80%. See, true one is 80. That means that when you get that distribution, okay, this is what they were trying to say there. See, then you have this distribution for thumb. Okay, this one is your y. See, when you draw the histogram, kind of like this, then you have the mean. mean is nothing but 60.1. Then you pick a data point which is 65.1, 65.1, and then say 65.1, 65.1. They were asking what is the proportion of data that's gonna be more than 65.1. See, proportion of data that is more than 65.1. See, 65.1. See, if you want, you can write like this: a proportion y greater than 65.1. See, mathematically you can write like that. See, PR stand for probability or proportion. See, same thing. Proportion or probability. See, 65.1. That's the same thing. Area under the curve more than 65.1. In order to find that one, we say that I go to thumb data. No, I'm gonna go to the fingers data. I'm sorry, fingers data, and create fingers data and create something called more than. They give a name more than 65.1. See, greater than 65.1. The new variable name is greater than 65.1. See, how do you find that one? Booleanly. You go to fingers and you're gonna pick thumb and see how many of them greater than this one. See, you check that one first and then assign to greater than 65.1 will be a Boolean one, whether true or false. Okay, then you're gonna make the tally. You make a tally. Tally for who? Tally for this guy. See, tally for this guy. Greater than 65.1 coming from data set which is fingers, and for the format you use proportion. See, the proportion that gave you the answer true values. See, true values, which is 0.20. That means 0.197, which is 0.20. See, 0.20. 0.20. See, 0.20. That means this area is 0.20. See, over 20%. Or there's a 20% chance that the next observation gonna be more than 65.1. You can explain that one in any way you want. See, and the same way when you're gonna write the tally, you can just say tally. If you want, you can simply go straight to the fingers and then greater than, rather than calling for data, then 65.1 comma format, because proportion, that would give you 0.20 or 20%. That means there is a 20% chance that the new observation is more than 65.1, not 50%, okay? Earlier 50% because we were talking about with respect to mean. But if by any chance, if it is more than 60.1, more than the mean, definitely 50%. See, we know that is 50%, more than 60.1. If the new observation is going to be more than 61.1, what would be the proportion? Proportion, no, the probability. PR stands for the proportion of probability. See, proportion, or you can see probability. See, probability. See, probability that that data. The data, okay, that data, okay, is okay, data is more than 65%. Okay, let's see like that probability. It's the notation. See, if you want, you can write like that. That's what they do. That's how you're gonna find the proportion. See, now what we're gonna do, instead of that working with this one, they jump into something called the normal distribution. This is a very theoretical probability distribution. They say that they believe that, as I mentioned, their distribution is, that means that the distribution coming from the error distribution. Error distribution. This is what I'm talking about. Okay, I'll explain this one. They think, okay, you can remember in our discussion, we had the population distribution and sample distribution. See, we had the population setting. In the population setting, we had a y equals, you can remember, mu plus epsilon. You can remember this one even given by beta naught plus. Its counterpart, we have y equals y bar plus e, or b naught plus e, or y hat plus e. See, you can remember this. Then we think about the error. Error is nothing but y minus mu in this case, which is epsilon. In this case, we call the residual. Residual is nothing but y minus y bar, which is e. Okay, or y minus y bar, or there's the same thing. Okay, for the same thing, we can write y minus b beta naught, that's epsilon 2. Here y minus b naught, that is e also, or y minus y hat, that's also e. See, then you get the error, and then you draw the histogram for error. See, residual. See, this is the residual histogram. See, residual histogram. You can draw. See, that's residual for epsilon. Okay, that's for epsilon. Then you had something like this. Then we can do this one for the residual too. See, then you can, not that one, but pretty much like that. See, something. This is so close to each other. See, because of that more points. See, this is error. See, this is residual. This is called the error distribution. It's the residual distribution, the sample setting. They say that theoretically, they believe we don't know the shape. Okay, we don't know the shape of this particular distribution. Only thing that we know that it may be coming from this residual distribution, may come from any kind of a distribution, not the symmetric. They believe, for their convenience, okay, it is a bell-shaped distribution. That's what they believe. See? They believe it's a bell-shaped distribution called normal distribution. Bell-shaped, not only bell-shaped, symmetric, bell-shaped distribution. It has a name, normal or Gaussian distribution. That's what they believe, with a certain mean. See, this is for error, epsilon. Okay, this is for epsilon. See, epsilon. See, the error, this one has a, this one is 0. We know that its mean is 0. Its mean is 0. See, that's what they are trying to explain through this. See, explained here. Okay, that's the kind of a discussion they are built in. That's why they say error with the normal distribution. This is a theoretical probability distribution. They believe that. It is not the case in, because we don't know about this guy. We don't know. We only know about this one. Why they assume, see, it's gonna be like this. That's the kind of a discussion they are building up over here. Okay. So see, they say the calculated probabilities from your sample distribution works okay, especially if you have a lot of data. But if you have a smaller amount of data, the shape of the distribution can be very jagged. Remember that back in chapter 3, when we were examining the distribution of die rolls, we simulated random sample 24 die rolls and came up with a distribution that looked like this. See? Doesn't have any shape. See? Look like that. See, if you don't want to use this distribution to calculate probability of the next die roll being of a 6, because we can do better. We know in this case the probability is 1 out of 6 because we have a good idea of what the actual DGP and resulting population distribution look like. But in this case, but we can remember our population one was not like this. It was a uniform distribution. Each and every number has a same equal chance of being rolled out. See, facing up. That means 1/6, 1/6. See, 1/6, 1/6, 1/6 for all the numbers 1 through 6. We have a 1/6 of chance. That's for the population. Population, it was uniform. We can remember that. See, it was uniform. We can remember. That's why they see. See, if we wouldn't want to use this distribution calculation because we have a good idea about what the DGP result and probability look like. Even though the sample distribution 24 similar die rolls doesn't look like uniform, we are pretty confident that actually came from a uniform distribution. See, it doesn't look like a uniform, but its population definitely coming from a uniform distribution. Okay. So see, in that case, okay, for that case, okay, we can pretty sure that it doesn't exactly. We bring this up because even the most of the time we read real data, we don't know what the shape of the population distribution look like. We don't know. We can be pretty sure it doesn't look exactly like our sample distribution. No, we know it doesn't look like the sample distribution. For this reason, and also to make calculation of probability easier or mathematical tractability, we usually note the distribution of error with a smooth theoretical probability distribution. The uniform distribution, which we used in the case of die roll, is an example of the theoretical probability. It's one of the distribution. Now they're gonna say, instead of that one, let's jump into the different kind of a distribution. The most common theoretical probability distribution used to model error is the normal distribution, often referred to as the bell-shaped curve. Even if the distribution of error in our data doesn't look like exactly normal, there are good reasons to assume that the population of the distribution error for many variables will be normal. See, even if this my sample distribution is any shape, doesn't matter. It doesn't look like this one. Maybe right skewed, left skewed, uniform, any kind of a shape, but we still assume that its population is coming bell-shaped distribution. That's a great assumption over here. In addition to that, we saw that in some cases you can even assume that they were uniform. For sure, it's gonna be uniform because of it is a fact, because when you roll a die the die has like a 6 sides. Each side, there's a chance of each side is gonna face up would be 1/6 because of the 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6 come together. You're gonna have a uniform distribution for that particular case. But in the most of the cases, even though you know that histogram or the distribution, the shape, you don't know how that population distribution look like. That's why they're gonna make, for the mathematical tractability and easiness, they come up with a certain distribution and say, let's use the normal distribution from now on. That's what they're trying to do for the population. Okay. So see, the most common theoretical probability distribution uses more than normal distribution. See, it doesn't look like normal. Okay. The reason for this is to do with the principle of aggregation. We saw scores on an outcome variable are pushed up and down by multiple other variables. Something that is frequently true for the variables we might be interested in. The distribution of the outcome variable tends to take on a normal shape. This process in which multiple independent variables get summed together is called aggregation, and the result in normal distribution has nothing to do with the variables. It is just a mathematical determined conclusion that the results from the aggregation process there. Okay? So they are trying to show there's something over here. That means we can demonstrate the power of aggregation with the simple simulation. Let's simulate a data. Okay, let's explain this. What do you mean by the aggregation and the normal probability distribution? See, we can demonstrate the power of aggregation with a simple simulation. Let's simulate data set with 1000 observation and 10 variables, each generated randomly from a uniform distribution, and each having possible scores of -3 to +3. We will start by simulating one variable using this code. See, variable 1, var1, resample. See, numbers gonna go from -3 to 3. You have to pick how many numbers? 1000 numbers. And then you call that one var1. And then see, put the var1 into data frame called the sum data. See, so when you get this one, you get this one and data frame. Wow. See, if you call some data, if you look at the first 6, and ahead of this one, okay, the first 6 numbers, they were picked in between -3 and +3. See, numbers. There will be 1000 numbers like that. What do you think that the distribution of var would like? See, like a uniform distribution. Why it's uniform? Because this is like a population. This is like a population. See, large number of data being that selected on that way. And then if you draw that histogram, so see, GF underscore histogram of var1 data or some data. See, let's get into from this range. If we increase this one, definitely it's going to be uniform. That means each number means that the numbers between -3 to +3 are all numbers -3 to +3, -3, -2, 1, 0, 1, 2, 3 would carry the same number of observation if you pick a large sample. See, uniform. See, roughly flat like a uniform distribution. See, you can see that. What is the data generating process of your look like? The function resample, which randomly pick one of the numbers between this one. See, this is a data generating process. This is how we're going to generate the data from the that particular distribution. Okay, we don't know the distribution, so we're going to go back and see that these numbers would fit into what kind of a population distribution. But in order to do that one, you really need the data points. You created 1000 data, and then you go back and fit that into a histogram, and then you show it is uniform. In order to do that one, this DGP means like in back can see that your population, what the population would be, is given by this code. Okay, that's what they say. So you're gonna resample. Okay, from this one resample. Resample means, can you remember? Without, you see. So with replacement, this one with replacement, you're gonna replace and put it back. In that way, you're not gonna short of any number. Whatever the number you used can be used again and again and again. See, like that. See, some numbers has been used two times, 3 times, 2 times here. In this particular, that out of 6 numbers, 2 numbers has 3 has occurred twice. That means it's been with the replacement, whatever you pick 3 has been put it back over there. That means that you cannot pick the 3 again. Okay, you know that. So if that sense that this is the way that how you're going to go ahead and by doing this one, this whole thing, resampling means you're going to go back and you're going to resample large number of data points and think like what kind of a shape would be given when you have the data and then draw histogram. That's called the data generating process. That's a uniform distribution. See, the uniform distribution for the population, not for the sample. It's not actually a sample. It's a very big thing, almost a population. Go ahead and make a histogram for VAR1 and see what it looks like. We already did that one. Okay. We already did that one. And then they say, do this one for how many times? 10 times. If you do the 10 times and then draw the histograms, they all looks like this. See? We do any of simulated variable one through look normal. No, most of them don't look like a bell-shaped curve. Look at, they all gonna go to what? Uniform. See? You did this one. You generated numbers. Through the numbers, you saw all not a bell shape. See, all uniform. Because we simulated a large sample of the 10 variables, and because we randomly each score from a uniform distribution, we can see that what, as we expected, each distribution looks approximately uniform in shape. Because that we pick these numbers from uniform distribution. Because you know that numbers are uniformly distributed. We pick the uniform. So as we expected, as we expected that we got a uniform distribution too. See? So, see, if you're gonna run summary statistics, see, we can also see from the histogram that the mean of the each variable is close to 0. See? Always, see? It's been centered around 0. You saw that. You saw the mean is 0. You know the reason mean 0 for that one. Okay. See, getting 0. The average. I'm not talking about the error. I'm not talking about the error. I'm talking about this -3 to 3 in a uniform distribution. Okay. To this discussion, same thing. If I get the same discussion, okay, same discussion, I'm going to get to the other side. And if I discuss with the aid of uniform distribution, then now in the population setting, I have a uniform distribution. Okay. In a uniform distribution, you have the starting point somewhere. They call the A. In this case, A is -3. Okay. And this one is B. That's a +3. How do you get the center? The mean. How do you get the center? You can get the center by thank you. Center by mean is given by A plus B divided by 2. So in our case, we have -3 plus 3 divided by 2. You get 0 divided by 2, which is 0. That's why it's 0. That's why in all the cases you saw, see, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 everywhere. See, you can see that expression, see. So we can also see from that 0 again and accelerator based on the code we used to simulate. You can use the R function summary to get quick summary of this one, see. See, they put everything into some data. See, all the variables. See, here, VAR1. See, histogram, this one. See, they get the variable 2. Resample again. Another one. var3, var4, var5, var6, var7, 8, 9, 10. And you're going to combine and put everything into one data frame. You see, these are the variables. You can remember. If you put this one as a variable, var1 going to go to the first column, var2 second column, third column, fourth column, fifth, sixth, seventh, eighth, 9, 10. You're going to have a 10 columns in a spreadsheet, and you're going to have how many rows? 1,000 rows. That's the data frame. See, put all the variables together. See, together, and then they're going to do this one at a time. See, one at a time. See, it's the data frame. Your data frame look like this. See, that data frame name again, some data. See, some data. You have a some data, and again they call them. They put it back to some data again. Then in the some data you have this one. Not only one, var1, var2, var3, var4. See, that's a data frame. See? Then we individually draw the histogram. See? And then if you go and run that some data, that each and every variable's summary statistics will be displayed. Minimum, first quartile, median, mean, third quartile, max, and pretty much everything. See, you can see that pretty much the mean. See, very close to 0, 0, 0, 0, 0, 0. See, 0, 0, 0, 0, and 0, sorry, 0, 0. See, now for the aggregation part, I see what happens if we make a new summary variable that is the sum of the 10 variables for each row of the data set. Now what we're going to do? We're going to add, see, the sum of the 10 variables for each row in the data set. See, I'm going to sum them up. How good are you going to sum the variables? See, aggregate. Can you remember the aggregate? We can remember that how we aggregate. You know, we're going to sum them up. See, if you want to aggregate, then you go to that one. See, you can say the sum. If you want the sum, you can say sum. You go to the variable. See, income data. Okay. Then you're going to draw that sum. You can do this histogram for the sum. What I'm going to do is try to write the R code that adds up to all 10 variables and save the sum as a variable in some data. So you need these variables. So this is my data set. Look like this. var1, var2, var3. I'm not talking about this way. I'm talking about this way. See, I'm adding this way. See, that's what they say. They say that row wise. See, this one. See, try see. Happen if we make a new summary where that is sum of the 10 variables. See, new variable sum of the 10 variables for each row. For each row. See, that means sum of the 10 variables. Sum. You're gonna sum up that variable this way. That means that you're gonna add this number. -2, -1, 1, -2, -3, -2, -3, -1, 2, 0. See? Like that. -1, they get cancelled out. See? -2, +2 get cancelled out. Then you're going to have how much? See? -2, -4, -6, -6, 4, 10, 11, -11, like that. Okay? So how do you get that one? So can you remember how we did that one? You're going to get everything. See, let's try this one. If you use the aggregate, see, aggregate of aggregate. can see not the bar one. Can do like this. Okay. I'm gonna do something like this. I'm gonna go ahead and say was variable for get the variable. Okay, I'm gonna get the variable combine into this one, all the variables. Already in this one. Okay, I'm gonna go ahead and do something. I'm gonna say head of put like a vector. It has been put into a vector. Let's say some data and record row wise, because this is gonna be done row wise through the within that data set. This data set we have data 1, data 2. I'll create something like this. See, V1, V2, V3. Okay. Or I can do in two ways. Okay, I'm gonna try something like this. My data, okay, head of some data, the some data, bracket, some data, close it close. Cut this one and run. Some data. See, okay, because of that, I'm gonna put this into a variable called var. Okay, I'm gonna put this into var, combine all this. Okay, v1. Okay, v1. Okay, v2. Two. Let's say we try this one for only 2. Okay, we can expand. Then I'm gonna go and write head of this one for some data on this one was this one. Why this one not gonna some data, some of the columns. It should work. V1. Why we don't have a V1? Oh, sorry. Not the V1. VA1. VA1. VA2. Okay. Was. This one was. This one was. Yes. So. Yes, that's the same setting. Okay, that's the same setting. So what I'm gonna do, that's for the record 2. Okay, then I'm gonna go ahead and apply some data within that was. Okay, I'm gonna close it and then go to margin. Okay, that means I can do that one with a one shot. Okay, margin. Instead of one, I'm gonna do row column wise. This one row wise. I'm sorry, row wise. Function called sum. Close it. Apply some data was. Then close here. Margin 1 function sum. Margin is missing with no div. Okay. Margin. Okay, this is the problem. They're very case sensitive. Margin. See. Look at this is the sum of the row. Oh, it's gonna go all the way to 1000. See, 985 to 1000. See, 985, 86, 87, 88, 90, 91, blah 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 1000. So this is the sum row wise. I mean, like I see, -2 plus -3. I'm talking about this way. See, that's what they were telling. See, not the column wise, the row wise, not the column wise, the row wise. Okay. So instead of that one, okay, what I'm gonna do, I had this one too. I'm gonna keep that one as the way that it is. What I'm gonna do this apply this one. This one you check that one, okay, how it works, and then they call that one was this thing. I'm gonna take out, put it here, apply to some data, and then I take this out, and I'm gonna get this one. Okay, and I get this one. See, I'm talking about. I'm gonna get the whole thing out and put it here, and cut this one, and let's run this one. See, let's run that one. See, I'm talking about. I'm not talking about that one. I'm talking about starting here. See, here. Okay, I'm gonna go to the up. See, when they generated that, it's not gonna give the same number. See, this time, okay, but it's gonna generate different numbers. See, this has been given column wise. See, you go to the sum data. See, and then do that one. So I'm gonna keep like this. I'm gonna take out this one. I'm gonna get out this aggregate as well. Take out this one. See, I'm gonna take out this one and get this one and then put it here. You can just go and then do for the whole set rather than get a certain subset. See, apply sum data margin. Then that means that you are doing the summation column row wise. Okay, and then draw the histogram for the sum. It's been saved back to this data, and see, and then run this. See, it's not exactly the same thing. It should be different. Okay, it should be different. See, this is, you can use this function, apply function, go to data set, margin. If you put 2, you're going to have that summation. I'm talking about this sum, not this way. In the data frame, they're not going to do this way. They go to the individually one by one, column wise. If you want that one, you can do that. That's not what they were looking for. They say go over here, and then if you do this one 10 times for the first entry, 10 times you did that one. Instead of you are doing 10 times, you're going to get the summation. See, summation, and see how it looks like. Look at how it looks like. It's getting closer to what? Normal, if you see this gaps like this in the histogram, often means that the default number of bins is too large. Arch default is 30. They try fewer bins, try more bins. Try to observe what's the general shape of this distribution that's common across these different ways of presenting the same number. See, you can then play with that and see, you change in the bins. See, histogram, some data. See, this is 30. See, try the change in the bin number to be larger than 30. See, 75 bins. See, this one 75 bins. Okay. Let's see this one. See, it's getting closer and closer and closer to what? See, will she? That's why they see. Who? Sum, okay? Sum. How do you get the sum? You got the numbers for the first entry in different ways. These different ways. Those numbers were added. I'm not talking about the sum of this one. Don't get confused, okay? I'm not looking for the average of this variable. No. This is a different technique, okay? So I'm adding the whatever that this number instead of this one, you go and generate it again another number. I'm not talking about the second time. For the first entry, in the second variable, first entry, there are some. If you individually draw the histogram for this guy, it's look like this. You see, it doesn't look like a bell shape. It doesn't look like a normal. But if you take this, instead of this guy, this guy, and then draw the histogram for these numbers, you have repeated this one several times. I'm talking about these are called the repetition. See, this has repeated the same setting, the same way you are generating 1,000 numbers. That process has been repeated 10 times. If it's the case, instead of taking the first entry, please take the sum of all the entries. If you take the sum of those entries, that sum will, okay, if it is coming around, if it has been done repeatedly with a large number of times, see, if it has been repeated, see, repeated, 10 times repeated with several observations. You pick observation within that one. This is what I'm talking about, okay? Don't get confused over here. This is what I'm talking about. This uniform is not enough, okay? I'm going to get into the other side. They say that if you they say that if you pick so the numbers, okay, -3 to, okay, -2, -1, 0, 1, 2, 3. From this one, you pick a sample, see. You pick a sample. A sample of, let's say that you see sample 1 of size 1000. Within this one, you have 1,000 numbers. Instead of having 1,000 numbers, see, you have 1,000 numbers. See? First number, second number, dot dot dot, thousandth number. Okay, thousandth one. Okay, you're gonna have. Then you pick another one. This one you call the var one. Second one, second sample. The of size 1000. It's called the var 2. As a first entry, second entry, third entry, dot dot dot, thousandth entry. You do this one 10 times. Sample 10. 10 of size 1000. See? You know, first entry, second entry, third entry, dot dot dot, the thousandth entry. It's going to be any number between -3 to 3. Okay, it's called the var 10. See? They say that instead of doing that one, this all can be, instead of that one, go to the first number. First number is the first number from var 1. See, first number. See, I can say v1 first number, v2 first number, v3 first number, add together, and v10 first number, and get something called 1. Okay, first entry. Second entry, go to v1 second number, v2 second number, v3 second number, v10 second number, and you keep going this one and go to the 1001. 1001 means you're going to get the v1. See, v1, see, 1001 from v1's 1001, v2 variables 1001, v3 variables 1001, v10 variables 1001. They say if you get, I'm going to put a star for that one, 1 star, 2 star, 1000 star. If you get distribution, if you draw a distribution for this guy, see, this guy, it look like I see uniform. See, uniform. You saw that one. If you draw the histogram for this guy, see, look uniform. You saw that one. If you draw histogram for this guy, uniform. Those 1000 numbers. But I have a new 1000 numbers called 1 star, 2 star. That see in this one, inside this one, see. 1 star may be any number, okay? 2 star means any number, okay? 1000 star means 1000th entry. For this one, if you draw histogram, it looks like this one. That's why they say it looks bell shape. It's getting bell shape. See, not uniform. That's what they say. See, it's uniform. See, getting bell shape. See, if you increase all the beams, it's getting to bell shape. See, what does the distribution of the summary variable sum generally look like? See, normal. It's getting to normal. See, as you can see, just aggregating multiple scores together caused the result in distribution to be normal in shape. None of the 10 variables you added together were normal. They all were uniform in shape, but the sum is almost perfectly normal. While a few randomly generated values might move each sum up, others will move it down. This results in a lot of sums that are clustered around the middle. See, this fact is what gives a confidence that the distribution error is normal. See, some see above and below. This is the same way. Can you remember? See, it's been centered around 0. This is very similar to the error. Error gonna behave like this. That's a very reasonable for you to just assume that your error terms are bell-shaped distributed in the normal distribution. Error terms are normally distributed with a bell-shaped distribution in the population version, because that's, you see, it's been centered around zero. See, this is very similar to that one. That's why they are trying to say that error distribution, your error distribution, you see, fitting the normal model to distribution of a data. See, error distribution. See, that's what we are trying to do over here. So here they are trying to conclude and say they think whatever we assume over here, this one. I'm not talking about this one. This one is very, very reasonable. This assumption is very reasonable. What is the assumption? What is the assumption? Here we have that assumption. What's that assumption? See? This one, see? Symmetric. Your error distribution, see? Error again, see? You can say population error distribution is normally, see, error is, or you can say population error is normally distributed. Normally distributed means it's going to behave according to a normal distribution. That's the big assumption. See, we proved that this assumption is very reasonable. See, very reasonable. See? With what? With mean zero, distributed with mean equals zero for sure for time. See? Now let's say that for given not only the error, regular that any distribution, how we can model that one with a normal distribution. See, that's what they are trying to do. You go to favorite statistics of this guy, fingers, you get the d-histogram, and then draw this one for that guy, and you put a v-line, x-intercept, you go to this one, and color blue. See, we can know how to do that one. And now you need this shape. How do you get the shape? You're gonna get this shape fitting into a smooth curve, the same thing I talk about in the very beginning. How do you're gonna add this line now? That's the new command. You draw the histogram, you put the vertical line, and then see, link with dist. You are looking for normal color, you can say blue. Params means parameters. What are the parameters you really need in order to talk about this guy? You really need the mean and the standard deviation. When you draw a smooth curve on the top of this one, okay, any for the histogram, when you scheme in the smooth curve, when you have a histogram, say, let's say this is y. I'm not talking about data for time being. Let's say that for anything, if you have a histogram, see, you have a histogram. When you draw a smooth curve scheme in this one to get a certain shape, or if you want to fit in into bell shape, if you want to fit, if the histogram is fitted into symmetric and bell shape curve, see, if you want to do like that, see, you can make sure. See, that's what they were trying to do. See, you really need to talk about this guys, that particular. If the histogram is fitted into this distribution, you must provide the, it's called the symmetric bell-shaped smooth curve. Okay, smooth curve. You must provide the smooth. You must provide the mean and standard deviation of the smooth curve. Smooth bell-shaped curve. You have to provide that for sure. That means you can say y is normally distributed with a mean of the value and a standard deviation of a certain value, whatever the value you put over here. Normally people like to write this one mathematically, y tilde n, they put the mean here as the value, comma, standard deviation, and close it. That's the mathematical way of writing. See? That's what they were asking when they are trying to put the smooth curve. That's the same thing. See, they have to, those are called the parameters. These two are called the parameter. This one, you know, the mean is a parameter. See, it is a parameter. It is for the population. This one also parameter. That's for the population. Okay. Now we have a trick here. Okay. Look at, as I said, y is normally distributed with mean. Since you don't have a mean, that this mean means population mean. Okay, that's why we call the parameters. Okay, population mean. You cannot provide population mean. You don't know the population mean. This is nothing but population mean. I'm gonna write it here clearly. Population mean. The other one is population standard deviation. You don't have population mean and standard deviation. Population mean. See, you don't have. Therefore, you're gonna substitute sample mean. Okay, that's the sample mean, whatever the value. Okay, whatever the value. And the other one is population standard deviation. Since you don't have that one, you put the sample standard deviation, which is the value here. See, right there. That's what we were doing over here. So since we don't have a population standard deviation in this list, we're gonna get that samples mean and the samples standard deviation, because this time we're gonna assume this thumbstat's gonna be like a data set, mean gonna be a variable inside that one. See, look at how we got the smooth curve. See, you might be thinking, the normal curve doesn't fit that well over the data. You are correct, but remember, our goal is not just to model our data, but to model the long-term results of DGP. See, we are not modeling this one. See, you might be thinking, see, we are not modeling this one, but we are trying to, DGP means data generating process, means we are trying to get a rough idea where this data is coming from. We really don't know that where they come from. Since we don't know, we're going to assume that it's coming from a bell-shaped symmetric distribution. To get that shape, we just did this kind of we ran this to R code. Other than that, we are not modeling data. See, our goal is not to just model our data, but to model the long-term results of DGP. Model the DGP. We want to get the DGP shape, not the shape of this guy. That's what they're trying to do here. Even when our data look jagged, the population distribution may not be. See, but to model the long-term results of the DGP, even when our data look jagged, the population distribution may not be. See? And the goal of a model is not to fit perfectly, but to balance the fit of the model with the simplicity and elegance of the model. By modeling error with the normal curve, we can trade in the complexity of 157 JAG values for an elegant 2-parameter model, the normal curve. See, we can trade that error can be traded with what? The complexity of this JAG value of an elegant 2-parameter model. See, that's what they say. By modeling error with the normal curve, this by modeling error. See, therefore that error, see, you're going to have an error, see, but to model the long-term result, see. Therefore, and the goal of model not to fit perfect, but to balance the fit of the model with the simplicity and elegance of the model. By modeling error with normal curve, yeah, we're only trying to do the modeling error with the normal curve, we can trade in the complexity of 156 Jack's values. See, look at those values. But see, like that, it never gonna be, see, like this. Even with that one, we can trade that one when we're gonna model in this one with this bell-shaped curve and thinking that where this data coming from with the like a normal curve fitting into a normal curve, we're gonna trade the complexity of this Jack value for elegant models, normal curve. Finally, remember our original question. We want to know the exact probability that the next randomly sampled student would have thumb length for more than mean. To help visualize this question, let's add one more thing, that graph, a red line to locate 65.1. So see, they put another line for that guy too. So this is the histogram. It's been linked with the vertical line at the mean, see, at the mean, see, with the color blue. Then you got the smooth curve, and then you're gonna see that how many data points gonna be more than 65.1, or the probability more than that one. You can do like this, see, you can do like this. With the aid of the normal distribution to calculate probability, now easy, see, you're gonna say that the thumb is represented by the black vertical line in the picture below. This one is 65.1, and see that how much proportion is gonna be more than that. Its corresponding C-score, 0.57 as well. Okay, you know that one. Based on the picture eyeball, the proportion of thumb might be at least see, 10%, 30%, not more than, not these two for sure, not 45. See, the center is here. So if one side is 50, the other side is 50. So it's gonna be around 30%. See. Now what? Because the normal distribution has a smooth shape easily defined by two parameters, R can tell us exactly probability by using the mathematical function for normal distribution. There's a function called XP norm. See, that would be very easy that because we are using normal distribution. Now you can go ahead and get the probability one shot, the exact probability, not the way that we used to do. We used to do with the tally. You don't need the tally anymore because we are assuming that our distribution is a bell-shaped distribution with a standard deviation is this much and the mean of this much. See, then you can say, see, you can put normally this a sequence would be that in order to find the probability. So this is how we're gonna find the probability in a normal distribution. Okay, this is what they were telling. If you have a now normal distribution, see, normal distribution. See, this is y. See, you know y is, see, let's say that it's mean. So you know mean would be 65 point something, no? 65 point something. No, not 65. I'm sorry. I'm gonna say that this is given by, mean is given by, okay, whatever the mean, see, it's given by, what do you call that one? Thumb stats mean, okay, given by thumb stat mean. Thumb stats mean, okay, and standard deviation given by thumb dot stats SD. You know that. Now if you have a 65.1 here, see, you can easily, I'm looking for probability that y is greater than 65.1. See, what's the chance that any data point is going to be more than that one? See, since we have a normal distribution, we have a new command called XP norm. See, it's called XP norm. XP norm, you put the value which is 65.1, then you have to give the mean as a sequence, mean which is thumb stats, go to $mean, and you need SD, go to thumb stat and go to SD. See, that's the sequence. See, that's the sequence. See, see, if you do that one, see, that would give you that. So the part related to green part, they will give you everything. See, more than 65 is the, see, green color, this one, see, here the color, see, red color. So when we model error with the normal distribution, we think about our data in a smooth way rather than a jagged way. See, it's been like this way. They say, no, we don't like this way. This based on the sample. We don't want to worry about the sample. We're going to look for the data generating DGP data generating process. Through that one, we just get a smooth curve to get a rough idea about how the DGP would be, that my population would be. Population is look like that, even though that my sample is a very jagged one, see, like all, see, go up and down like they're not smooth. But with the aid of that one, we can tackle the whatever the question we have. See, that's what they do. See, they're probably using this distribution. This is the way that how we do. So when we do this one, if we are interested in the probability of a student having a thumb longer than this one, what's the part of the picture about should we look at? The green part. According to the normal model, what is the probability of student having a thumb longer than this one? 0.28. 0.28. 28%. You probably notice that the border, the black line representing me, not labeled 65.1. Instead, it is labeled Z.57. What does this C-score mean? C-score, you know that. That's a C-score related to that guy. That's a number of standard deviation, the fit between the mean and 65.1. That means how far this one from the mean, that's 65.1, or that it's C-score, okay? A C-score. It's a C-score. See, there's more and more normal distribution, see? Different kind of normal distribution. See, but if they were not normal, you go ahead and then look for that some kind of a, see, if you have in this game, you do that one, see. So here, see, by now you see the binormal distribution are often good model for your aggregation of forces, and also how you might use them to make prediction. But why is the distribution that look very different from one another called normal? The shape of the normal distribution is intuitively like a bell, but it's considered what they really means, okay? To more concrete, let's go back to Kaggle, okay? Kaggle, our favorite video game, see? Remember what we had that friend who scored 37,000 points in Kaggle, see, shown in the red, and we were trying to evaluate how skilled the player she was. When we discovered that the bottom distribution, where the standard deviation is about 5,000, was the actual distribution of Kaggle score, we were less impressed than when we were thought it was the top distribution. As it turns out, the top distribution with the standard deviation 1,000 is from the game called Kaggle. See, this one is more data points are more, see, clustered around the mean in that way that it's this C-scores you can calculate when you calculate the C-score, see, and the error and everything, see. They both would have the normal shape distribution, see. Doesn't matter, we're going to consider like a normal distribution, okay. These are just basically what we're going to do. I think this is pretty much same thing. If you go to this one and talk about the empirical rule, what they're going to say, this is very interesting. I go straight to the empirical rule. Empirical rule says, okay, empirical rule means They say there's a rule that can be used for this bell-shaped distribution, empirical rule, okay, or golden rule, or sometimes called the 68, 95, 99.7. Some people call it 99.7 rule, okay, rule of thumb. See, only for bell-shaped distribution. Only for bell-shaped distribution. That means what they say. There's a very interesting thing on this one. This is your, let's say instead of working with X, I'm going to work with Y, we're going to work with Z, okay? C-score. As I mentioned, C-score always have the middle 0. And then you have a, see, this point. Actually, as I said, standard deviation is 1. When, see, this is mean. When you convert it into C-score, standard deviation is always 1, mean is 0. This point, mathematically, there's a point called the point of inflection on both sides. Inflection, both of inflection means neither minimum nor maximum. That means that some places, see, falling down, hit on a point and rising up. This is called, see, minimum. Sometimes rising up, hit on this point and falling down. That's called the maximum. Sometimes falling down, going through this one. Or rising up, see, rising up and see, rising up. Go this way or this way. Or rising, falling down, or rising up through this point. These are called the points of inflection. Neither minima nor maxima. Fluxion. Okay. Inflection. Okay. Inflection. See. The distance between the mean and this one is actually called the standard deviation. That's the physical interpretation. Okay. That means this should be 1. On this side, this should be negative 1. See? What they say according to this rule, they say that any data falls within 1 standard deviation. See, within this one and this one, 1 standard deviation is how much? 68.26% data. See, that means 68.26% of data fall within 1 standard deviation. See, and if it is 2 standard deviation, see, let's say now 2, minus 2 to plus 2. That's a within means minus 2 to plus 2. This is me. This one is nothing but 95.44%. 95.44% of data for within 2 standard deviations. So the other one is, you see, pretty much everything gonna be within 3 standard deviation. 0, minus 3 to plus. This one will cover 99.73. That means all data. 99.73% of data fall within 3 standard deviation. That's what the golden rule is. See, that means that when you have any calculations, you can calculate easily by based on this property. See, look at this one. I don't think this one we really need to go through that one. That part, this part is okay. See, the distribution above, we have shown that the light gray line illustrate the boundaries of zone 2. See, that means within second standard deviation. So that means, see, the unlikely part, the part is the 0.05 part. See, this one, see, this one, this line. If they are talking about this line, see, the unlikely part is that this one, 0.05 part that is farthest away from the mean in both left and right direction. Label the region below with the appropriate proportions. See, they say the 5%. 5% from these two tails are taken out. If 5% are gone, see, in the middle, see, part is the point of part that is furthest away from the mean. See, label the region below with the appropriate proportion. See, 95%. See, instead of that one, see, what they did was here, okay, see, they went to this one and they keep 95%. See, you can remember 95% earlier. It is roughly 95%, but 95%. They say that the rest, which is 5%, should go, which is 0.95. And here should be then what? If it is 95%, this should be 5%. 5% means 2.5% on this side, and 2.5% gonna go to this side, see, which is 0.025, 0.025. See, and go to both sides. That's what they say. See, that's what they say. So see, 9 if 95 in the middle, see, second on 95, 0.025, 0.045 gonna go to the tail. See, that's the end of the chapter. I mean, like that's something, see, you can think about that, how we develop this one. The error term has been explained by a normal distribution, which has a properties of bell shape, symmetry, and within one standard deviation, they contain 68% of data, roughly. Within two standard deviation, 95% of data. Within three standard deviation, 99.7 of data. That means data means, what that means, this is 99% 73 or 68.26 means that this is a number of data points, the area under the curve, or this is the probability, this is the proportion. Proportion, probability, chance, area, same thing. How much? 68. That means 68 of data. If you have 100 data, definitely, if they can be fitted into a bell-shaped distribution, 68 data points gonna be within -1 to 1. When this, I mean, like converted into C-score, okay? When we convert it into C-score, okay? Okay. See, if not, you can use it like that. But if you have from the same thing within two standard deviation, there would be 95%. 95 of data points going to be out of 100 going to be within -2 to 2. And pretty much everything's going to lie between -3 to 3. That's what they say. When you take them, this 95%, you're going to have that 2%, 25, 2.5%, 2.5%. That means altogether 5% being taken out. See, on the from the tails. That means 95% gonna go to the middle. So that means here 2, this is -2 roughly. See, can you remember -2 to 2 will cover 95%. See, right there. Okay, that's the end of this chapter. And then if you have any questions, just email me. And then if you're working on that, your homework, quizzes, and everything. And then if you want, you can then set up like a one-on-one that help session even. But let me know that, okay, I'm more than happy to help you guys. And then I want you, everybody to get the best grade in this class and then finish happily, okay? And the learn material, coding, learning material, and the theoretical aspects, and then how that can be utilized in the data analytics at the end of the day, because this theoretical background very important later on for you to move forward and then build up the heavy stuff later on, okay? So the programming is a key part, and then we can see you guys on Monday. Until then, you guys have a good night and then stay safe and be well. Take care. Bye bye.